Welcome to the office. We want to take a look at finitely generated groups. And to do that, we're just interested in investigating a definition and a theorem here. So this definition really just is reflecting what we had discussed for the introduction to this section. So if we wanted to talk about the subgroup generated by two elements, then we're talking about this, right? What does this create? And it works out to be the smallest subgroup that contains those two things, much like we said this is the smallest subgroup that contains this thing, right? What this generates is exactly the small subgroup that contains that. Same thing here. This is the smallest subgroup that contains these, and we can obtain that by taking combinations of these particular elements, working within whatever operation is defined on that set. So the smallest subgroup containing that is the subgroup that's generated by that. Okay, cool. I think that's pretty straightforward. If it happens to be all of G, then we say that those things are the generators of G. And if there is a finite set that generates G, then G is finitely generated. So pretty straightforward there. What we end up with is, what could we do here? Well, let's look at the theorem here. So if G is a group, and this collection of items, right? Because I is in an indexing set. So if we have this collection of elements that are in G, then the subgroup generated by that has elements precisely those elements of G, right? So it's elements of G that are finite products of integral, so integer powers of the individual AIs, where powers of fixed AI may occur several times in the product. So what we're saying there is to talk about this, if I wanted to talk about the generation of Z12 by using the elements 2 and 3, like we saw earlier, I could have 2 plus 2 plus 2 plus 3, which we can represent as 3 times 2 plus 3. Okay, so generator. We could also look at 2 plus 2 plus 2 plus 2 plus 3 plus 2 plus 3 plus 3. And this works out to be, now we know that addition is commutative, so it seems a little bit silly here, but this is 4 times 2 plus 1 times 3 plus 1 times 2 plus 2 times 3. Now, if it weren't commutative, then I couldn't change the order here. Since it is, I can regroup these and life is good. But there are instances where it's not commutative and we don't have the ability to reorder them. And this, if it's not commutative, would generate something different than 5 times 2 plus 3 times 3, okay, if it's not commutative. In this case, it is, so we could have just rearranged it. Fantastic. So, but that's what it's saying here, integer powers of the individual things, and the powers may occur several times in the product, or powers of a fixed thing. So, oh, look, it appears here and it appears here. That's okay. 2 doesn't have to appear in one place. 2 can appear in 2 different places, or 3 different places, or 10 different places. Commutativity would allow us to express it as one, but it's not required, especially for those groups that are not commutative. Excellent. So this again is an example that we saw earlier. There are other examples. The Klein 4 group, okay, E, A, B, C. This group was discussed back in section 5. In an example, we looked at the table. And if I wanted to, I can look at what's generated by A and B. Okay, A and B will actually generate all of V, because A times B gives me C, and A times A gives me E. So I can get the remaining 2 elements. However, if I were to consider just the set A, that is, right, this generates A, and that's just E and A, because A squared is E. So E and A. So it generates a subset. If we add the other thing, then it generates the whole thing. 2 and 3 generate the whole thing for Z12. So there are some examples. If we wanted to, we can recognize that infinite groups can be finitely generated because 1, for example, generates all of Z. However, there are also infinite groups that are not finitely generated. Q, for example, that is the rational numbers, is generated by, so this is where it gets a little bit weird. We can generate this by the set 1 over n, for n being in the natural numbers. And this is under addition here. So natural numbers, positive integers rather. We don't want 0 there, of course. And we assume that we can take 0 times that to get that. But then if I take 1 over n plus itself n times, then I get 1, and I get all of the integer values, and then any linear combination is going to give me any of the fractions that I desire. So so it's certainly generated by this. I could have actually said 1 over n, where n is prime. That would have been reasonable as well, because then I can take, well, actually, got to be careful about that because I'm not taking products. So this certainly generates all of the rationals anyway. So finitely generated, not finitely generated. If I were to consider all of the units for our complex numbers, right? So this is a subset of the complex numbers, subset of the complex numbers. There we go. I'm looking at a subset of the complex numbers, the units here. This is also not finitely generated, but the generating set is also not countable. Okay, so finitely generated, generated by a countable set. Set of units would not even be generated by a countable set. It's an uncountable set that generates it. So very, very different scenarios that we have here. Anyway, I think that takes care of what we need for a discussion on that. Let me know if you have any questions, and have yourself a wonderful day. Thank you for joining me.